Good morning. Today, we are going to present our final Algoritmics2 project, an intelligent university regulation search engine. The idea behind the project is simple: to allow a student to find specific information from the university regulations by making a query in natural language. For example, what happens if I do not pay my tuition on time? To answer this type of query, the system identifies the keywords and searches for the related articles, displaying both the information found and the corresponding titles. The initial proposal we were given consisted of going through the entire regulation for every search. This worked, but it was not efficient. Therefore, we proposed an improvement using an inverted index, which allows us to directly find the articles related to the keywords without going through the entire regulation. This makes the search faster and more efficient.
First, let's see how the original proposal works. The user enters a query. The system divides into words, remove punctuation, and remove common words, such as connectors, pronouns, and articles. The remaining words were stored in linked list. Then the system went through every article of the regulation and shared it for matches. The problem was that this process was repeated for every query. With only a few articles, it can work well, but as the regulation becomes larger, sharing the entire document for every query becomes more expensive. We also found other problems. The structure used to store the regulation was more complex than necessary. There was no ranking of results, and the system was not flexible for roving or adding new regulations. Also, a large part of the logic was inside only one class, which made the code more difficult to maintain and expand. So we asked ourselves, how can we make the search faster and the system easier to maintain?
Our solution uses an inverted index. It connects each word with the articles where that word appears. The main components are regulation. Organizes the regulation into titles and articles. Hash table handles the stopbots and helps avoid duplicates. Inverted index stores the words and their locations inside the regulation. Match counter records the matches for each article. Query engine manages the query process and generates the results. To store the locations, we use vectors which allow us to access the data efficiently. With this architecture, each class has a specific responsibility and the system is modular.
To improve the search, we implement a hash table. A hash table is a structure that connects a key with a value. It uses a hash function to convert a key, for example, a word, into a position in the table. This allows us to search and access data in an average time of 01. In our project, we mainly use it for parts. First, for the stop words. When we process a query, we use the hash table to quickly check if a word is an article, pronoun, or connector, and then remove it. Second, in our inverted index, the inverted index class uses a hash table to connect each word with the articles where it appears. For example, if we search for the word Triton, we can directly access the articles that contain this word without searching through the entire regulation. Third, we use another hash table in math counter. Here we store the article location as the key and the number of matches has the value. This allows us to update the counter quickly. Finally, when we build the index, we use temporary hash table to avoid adding the same word twice in the same article. Regarding complexity, building the index requires going through the words of regulation ons. So the cost is on, where n is the number of words. For a query, we share for each word in the index and process only in occurrences. If p is the total number of occurrences found, the cost is approximately of p, considering an average of O1 for hash table operations. The difference from the original proposal is that before we had to search through all the articles for every query. Now we build the index ons and reuse it, making the queries much more efficient.
We look at include where we have the declarations as RCRE, where we have the implementations and tests, where we check that the system works. First, we have article, which represents an article, title, which groups the articles, and the regulation, which contains the entire regulation. These classes represent the structure of the information we are going to search. Then we have free layer, which is responsible for reading the files. Common words, which filters common words, and hash table, which helps us perform fast searches and avoid duplicates. The most important part is inverted index. Here, we associate each word with the articles where it appears. So when we perform a search, we don't have to go through the entire regulation. Instead, we go directly to the related articles. All of this is coordinated by query engine. It receives the query, cleans the words, removes stopwords and duplicates, searches the index, and counts the matches with match counter. This allows us to obtain the most relevant results. Then we have regulation parser, which takes the text file, identifies the titles and articles, and organizes them inside regulation. In main, we have the system menu. From here, we can browse the regulation, perform searches, use the ranking, and look up specific articles. Finally, we have some tests to make sure the searches work correctly and to measure their performance. The overall flow is we read the regulation, structure it, build the index, and use that index to find the articles we are looking for.
Let's start with the demonstration. In the data folder, we have the two regulations used by the system, the general regulation and the specific regulation. First, we selected the opinion to see the loaded regulations. Here we can check how many titles and articles each regulation has. Now let's make a search. We select the general regulation and enter the following query. Who is the thesis advisor? The system extracts the relevant words from the query: professor, advisor, and thesis. Then it searches for these words in the inverted index and show the articles that match. We can also see information about the search, so as the number of words found, of number of matching articles, and the execution time. We select on one of the results, for example, article 17 of title 6, and we can see its complete content. Now, let's try the ranked search option. We use the same query and request top 3. The system ordered the result according to the number of matches and show the three most relevant articles. We can also select one of these results to see its content. Finally, we have the option to search for a specific article. For example, we enter title 9, article 28, and the system directly shows its content. Finally, we have the option to exit the program.
To conclude, we changed the original proposal into a search system based on an inverted index with ranked results and a more organized code structure. We improved the data structures to make searches faster and to support both regulations. The system was developed in C++ and meets the project objectives. In the future, we could add features such as synonyms and lemmatization to improve search accuracy. Overall, our solution meets the requirements and improves on the original proposal.